Okay, thank you, and welcome to the third lecture in this series. So you'll recall at the end of the first lecture, I forgot to take my mask off again. Okay, so recall that at the end of the first lecture in this series, we introduced two different population models involving selection. And I want to return now to the first of those two population models, which was introduced by Brunet, Derrida, Mueller, and Meunier. So in this model, the size of the population is fixed at capital N. It's a discrete time model with non-overlapping generations. Each individual has exactly k offspring, where k is some fixed integer that's greater than or equal to 2. And each individual has a fitness level, and the fitness of each offspring is the fitness of the parent plus some independent random variable with some distribution, say nu. And so there are then k times n offspring, but the population size has to stay fixed at n. So we just choose the n offspring with the highest fitness to survive to form the next generation. Now, Brunet, Derrida, Mueller, and Meunier studied this model non-rigorously in great detail. And among their conclusions were the following three results, which I'm calling conjectures because they were not aiming for rigorous proofs. The first conjecture actually goes back to earlier work of Brunet and Derrida. Let's let R sub m be the maximum of the fitnesses of the individuals in generation m. And then R sub m divided by m converges as m goes to infinity to some limit v sub n. And we can think of v sub n as being the velocity of the fitnesses. It's the rate at which the fitness of the population increases over time. And so their conjecture is that these velocities v sub n, which depend on the population size, will converge as n tends to infinity to a limiting velocity v sub infinity. And furthermore, the difference between v sub n and the limiting velocity is asymptotically a constant over log n squared. And this conjecture was proved in this model by Berard and Guerre in the case when k is equal to 2. They did need some regularity conditions on the distribution mu that governs the fitness distribution. Second conjecture is that if we choose two individuals at random from some generation and trace their ancestral lines backwards in time, then the number of generations that we have to go back to find a common ancestor of these two individuals is of order log n cubed. And third, they conjectured that if we sample lowercase n individuals from the population in some generation and trace their ancestral lines backwards in time, the merging of these ancestral lines is governed by the Bolthausen-Schnittmann coalescence. So what we want to do is to establish rigorous versions of these three conjectures. And we'll do this not for the original model, but for a model that's based on branching Brownian motion with absorption, which we will use to approximate this population model. Before we go back to branching Brownian motion with absorption, I want to mention a variant of this model in which it's possible to see directly that the Bolthausen-Schnittmann coalescent describes the genealogy. This model was also proposed by Brunet, Derrida, Mueller, and Meunier. We again assume the population size is fixed at n and generations do not overlap. But instead of each individual producing k offspring, each individual produces infinitely many offspring. And an individual located at x produces offspring at the locations x plus y sub I, where the yi's are points of a Poisson point process on the real line, whose intensity is given by e to the minus y dy. And then the n rightmost particles, that is the n particles with the highest fitness, are the ones that are selected to form the next generation. Now with this setup, we can see that the offspring of a particle located at x are the points of a Poisson process with intensity e to the x times e to the minus y dy. And therefore, if the n individuals in some generation are located at x1 through xn, the probability that a particular individual located at y in the next generation is descended from the individual at xi is exactly e to the xi divided by this sum, regardless of the value of y. So the fraction of the population descended from the individual at x sub I is proportional to e to the xi. Those points x1 through xn themselves came from a Poisson process whose intensity was proportional to e to the minus y. And so one can ask, what's the probability that we see one of these individuals such that e to the xi is bigger than z? Or equivalently, xi is bigger than log z. And it's going to be proportional to e to the minus log z, which is 1 over z. And as we saw in the first lecture, that 1 over z is the signature of the Bolthausen-Snettmann coalescent. And with some more careful calculations, one can show clearly that the genealogy in this population is described by the Bolthausen-Snettmann coalescent. But let's go back now to branching Brownian motion with absorption. Recall that we begin with some configuration of particles on the positive real line. Each particle independently moves according to one-dimensional Brownian motion with a drift to the left of rho. Each particle splits into two at rate 1, and particles are killed if they reach the origin, which in this setting we want to think of as modeling selection. The fitness of a particle corresponds to the fitness of the individual, and killing the particles at the origin kills the particles whose fitness gets too low, just as in the population model that we indicated. Last time we stated this result of Keston, which is that branching Brownian motion dies out with probability 1 if the drift is greater than or equal to the square root of 2. And if the drift to the left is less than the square root of 2, there's a positive probability that the process survives forever. In the previous lecture, we focused on the case when the drift was supercritical, so that rho was less than the square root of 2, or subcritical, so the drift was greater than the square root of 2. But what we want to focus on now is using this process to approximate a population undergoing selection. And we want this population to have a size that stays of order n over time. And so for that, we want something much closer to critical. But because the process dies out in the critical case, the best way to model a population whose size is approximately fixed is to choose the drift that's just slightly smaller than the square root of 2, so that we're in the case where the drift is slightly supercritical. And the results that I present on this model will be based on joint work with Julian and Nathaniel Beresticki. Now, to fully define the model, we need to specify the drift rho. And it turns out that to keep the population size as stable as possible and of order n for a long time, we want to choose the drift to be the square root of 2 minus 2 pi squared over log n plus 3 log n squared. So that's slightly less than the square root of 2. It's actually the square root of 2 minus a correction, which is of the order 1 over log n squared. We'll see later where that drift is coming from. Now, with this formulation of the branching Brownian motion process, where we give particles a drift towards the origin and kill particles at the origin, we don't actually see a traveling wave where the fitness of the population increases over time. But notice that just up to a simple translation, our model is equivalent to one in which there is no drift, but at time t, particles are killed if they reach rho times t. And in that process, we can see that we have sort of a traveling wave that's advancing at a speed of rho. And so that tells us that in our model, we can interpret the drift rho that's required to keep the population size as stable as possible over time as being the speed at which the fitness of the population increases over time. And consequently, the fact that this correction term is of order 1 over log n squared is in fact very closely related to the first of the 3 conjectures that I mentioned earlier. So now that we have our model, branching Brownian motion with this slightly supercritical drift and absorption at 0, I want to work towards stating the main results. And for this, we need some notation. So this time I'm going to let m sub n of t be the number of particles at time t. I previously called that n of t, but I don't want to get confused with this other n. x1n, x2n, and so on will be the locations of the particles at time t. I'm going to let L be this quantity here, 1 over the square root of 2 times log n plus 3 log n. We'll let yn of t be this sum. So we're taking a sum over all particles at time t, and a particle located at x is contributing e to the rho x to the sum. Then zn of t is going to be this other sum, where we have this indicator here so that we're only considering particles to the left of L, and we have this sine function which reduces the weight of particles that are close to 0 and close to L. And as we will see shortly, Zn of t turns out to be a useful measure of the size of the process at time t, if we disregard particles to the right of L. And so here's the main theorem which describes how the number of particles evolves over time. So we'll make two assumptions on the initial conditions. We'll assume that Zn of 0, that's our measure of the size of the process at time 0, divided by n log n squared, converges in distribution to some limit measure nu. And we will also assume that yn of 0 over n log n cubed converges in distribution to 0 as n goes to infinity. That's basically just preventing us from starting out with a particle that's near or to the right of L. And then if we consider this process Mn, which keeps track of how the number of particles evolves over time, then the finite dimensional distributions of these processes converge as n goes to infinity to the finite dimensional distributions of Nevers' continuous state branching process, which has branching mechanism A times U plus 2 pi squared U log U, where A is some constant whose value we actually don't know. A few things to note about this result. One is that we saw in the first lecture that Nevers' continuous state branching process is a process with jumps. So even though only one individual is born at a time in this in the branching Brownian motion model, we nevertheless get these jumps in the limit because there are some events where we have many individuals born at approximately the same time. Also, the scaling here is important. Notice this spatial scaling is 1 over 2 pi n. And that's telling us that this n log n squared scaling is the right scaling in the initial condition if we want to model a population of size n. And the time scaling is log n cubed. So that tells us that the time between these large jumps of the process is of the order log n cubed. And of course, that is confirming the second of the three conjectures that I mentioned earlier. Because of the connection between Nevers' continuous state branching process and the Bolthausen-Snittmann coalescent, which I mentioned in the first lecture, that previous result would lead one to expect that the genealogy of the population in this model should be given by the Bolthausen-Snittmann coalescent. And that's the content of this theorem. We make the same assumptions on the initial conditions that we had before, as well as assuming that this limiting measure nu assigns no mass to 0. Then we will fix a positive time t, sample n particles at random from the population at time t times log n cubed. And then we'll let psi n of s be the partition of 1 through n, such that two integers I and j are in the same block of the partition, if and only if the ith and j sampled particles have the same ancestor when we look back to time t minus s over 2 pi times log n cubed. And then the finite dimensional distributions of these processes psi n run for time 2 pi t converge as n goes to infinity to the finite dimensional distributions of the Bolthausen-Snittmann coalescent. Now, what is perhaps most notable about these results is that we do get these jumps in the process when we look forwards in time, which lead to multiple mergers of ancestral lines when we look backwards in time. And so before we proceed, I want to describe the key heuristic that explains why we get this behavior. What happens is that on rare occasions, one particle moves unusually far to the right. And when this happens, a large number of descendants of this particle are able to survive because they can avoid being killed at the origin. And in the end, this can lead to a substantial increase in the total number of particles, as a substantial fraction of all of the particles are descended from that one particle that drifted unusually far to the right. And all of this can happen very fast, much faster than the log n cubed timescale. And that's why these events show up as jumps in the size of the population when we look forwards in time, and as leading to simultaneous mergers of ancestral lines when we look backwards in time. So the basic strategy that we're going to follow from the proof is to find some level L such that a particle has to get close to that level L in order to give rise to one of these large jumps in the total number of particles. We will then consider branching Brownian motion with particles killed both at 0 and at L. And we will show that for this process, it behaves in approximately a deterministic way. That is, the number of particles is staying close to its expectation. And we can see that by using the kinds of first and second moment arguments that we described in the previous lecture. And then we have to separately determine the contributions of the particles that reach the level L, because those are the ones that are responsible for the jumps in the process. To carry out this kind of truncation argument, we need to have a very good understanding of branching Brownian motion in a strip. That is, branching Brownian motion when particles are killed both at 0 and at L. Let's actually first consider just one Brownian particle, started at, let's say, X, and killed when it reaches either 0 or L. And we'll let PT of xy be the density for the position of this particle at time t. I've put density in quotes because the integral of the density will be strictly less than 1 since the particle could be killed before time t. So this density is going to satisfy the usual heat equation that the density of Brownian motion satisfies, and it will have these boundary conditions that the density is 0, both at the origin and at L where the particles are being killed. Look for solutions to this equation of the form e to the lambda t times h of y. Some algebra tells you that, that the function h would then have to satisfy this second order ordinary differential equation here, and it would have to be 0 at 0 and at L. Solutions to this equation are given by the sine functions. H of y equals the sine of n pi y over L, and then lambda is equal to pi squared n squared over 2L squared. And so we see that we can write the density as a linear combination of these functions. So the density PT of xy has to take this form here, but we still have to identify these constants an, which are going to depend on the location x of the initial particle. In particular, because we're starting from one particle at x, the density has to converge to a unit mass at x as t goes to 0. Now, suppose instead of starting from one particle at x, we chose the initial particle at random from some smooth density f. And f of then p0 of y, the density at time 0 would just be f of y. And since this exponential goes away when t is equal to 0, f of y would just be the sum of an times the sine of n pi y over L. And by the orthogonality of the sine functions, one can calculate that if we take the integral of f of y times the sine of n pi y over L, then all of the terms in this sum, except for the nth term, are going to vanish, and we're left with a sub n times the sine squared of n pi y over L, which is L over 2 times a sub n. But of course, we really want to start with one particle at x. So on the left-hand side here, we really want to interpret f of f as being like a delta mass at x. And so that what we really have on the left-hand side here is the sine of n pi x over L. And that means that a sub n is given by 2 over L times the sine of n pi x over L. That completes the derivation of this density for the Brownian particle in a strip. Now we want to include branching at rate 1 and a drift of minus rho back into this process. And we can do that pretty easily by multiplying the density by a Gersonov factor to account for the drift. And then invoking the many-to-one lemma from the previous lecture, we can multiply by e to the t to account for the branching. And here again, by the density for the branching Brownian motion, what I mean is that if A is a subset of the interval from 0 to L, then the expected number of particles in the set A at time t is given by integrating this expression qt of xy over the set A. Now, I should mention that one could have derived this in a different way. I did this in a fairly probabilistic way by using Gersonov's theorem to account for the drift and the many-to-one lemma to account for the branching. But an alternative is that instead of starting from the heat equation, we could have just started from this partial differential equation here, where this rho times the derivative of q with respect to y would incorporate the drift, and this extra q term would incorporate the branching. Either way, this density is a little bit awkward to work with because of the infinite sum. However, notice that if t is much larger than L squared, then the first term is going to dominate this sum. So in the long run, we can approximate this density pt of xy, well, we can approximate qt of xy by its leading term, and we can get this approximate formula here for qt of xy. Here is this, again, this approximate density formula for branching Brownian motion in the strip. And so what can we learn from examining this density formula? Well, first notice that only this exponential term here involves t. So in particular, if 1 minus rho squared over 2 minus pi squared over 2l squared is equal to 0, then the exponential term goes away, and the density for this approximation to the density does not involve t at all. And in fact, we have chosen the drift rho precisely so that this equation holds. This is the choice of the drift that will keep the number of particles in the system as stable as possible over time. We don't want this to be exponentially increasing or exponentially decreasing. Also, notice that the density is proportional to e to the rho x times the sine of pi x over L. And so if we had a configuration with many particles at time 0 and summed over the particles, we would get an expression proportional to Zn of 0. And so it's, and this explains why it's Zn that's the best measure of the size of this process. It's Zn of 0 that determines how many particles are likely to be alive at some point in the distant future. In fact, if we choose rho to satisfy this equation here, and we do kill particles at 0 and at L, this process Zn turns out to actually be a martingale. Yes?
Just a quick question to see if I understood correctly. So this is still supercritical, right? So the total number of particles will in expectation still grow exponentially, but this is just the expectation of the number of particles in the strip, and that is stable.
That's right. So if you take the number of particles in the branching Brownian motion with absorption, then it will still be slightly supercritical.
Yeah.
But if you choose this drift and this value of L and you kill particles at the right edge, then you're going to get something that's critical. Exactly. Okay, and then the other observation that we want to make here is that the density formula here is proportional to e to the minus rho y times the sine of pi y over L. And so what that tells us is that no matter what initial configuration of particles we start with, if we wait a long enough time, in particular much larger than L squared, which is the same as log n squared, then the particles are going to settle into a fairly stable configuration where the density of particles near y is going to be roughly proportional to e to the minus rho y times the sine of pi y over L. So we're now ready to explain the choice of L, which still should seem mysterious at this point. So suppose we were to place n particles between 0 and L at random according to this density here, which, as we've seen, gives a roughly stable configuration of particles. Well, then you can just make a calculation and see that Zn of 0 is of the order n times L squared. Now, let's say a particle gets close to L, let's say to L minus 1. And then the contribution to Zn from this particle is e to the rho times L minus 1 times the sine of pi times L minus 1 over L. When L is large, this sine term is going to be of the order 1 over L. And so this whole expression is of order 1 over L times e to the rho times L. And notice that because rho is roughly the square root of 2, this expression is going to be the same order of magnitude as n times L squared, precisely when L is within a constant of 1 over root 2 times log n plus 3 log n. So that's why we made this choice for L, which in turn gave us the choice for the drift rho. The point is that if a particle gets to within a constant of this level, the jump in the number of particles that is produced by descendants of this particle is going to be the same order of magnitude as the total population size. And so those are the particles that we want to remove from the process and consider separately. One can also understand at this point the log n cubed timescale. Again, let's just place n particles between 0 and L according to this density. If there's a particle very roughly between L minus 1 and L, then it has a decent chance of hitting the right boundary before time 1. So one can just calculate the expected number of particles between L minus 1 and L. It's just the number of particles times the integral of the density from L minus 1 to L. And you just compute that this is of order log n to the minus 3. So the expected number of particles that hit the right edge in one time unit is roughly of order log n to the minus 3. And so the time that we have to wait for a particle to hit the origin is of the order log n cubed. Now, even with this truncation argument, killing particles at 0 and L, the truncation argument is quite tricky. So typically when we want to do truncation, we're hoping for two things. Number one, we hope that particles don't actually hit the boundary, or perhaps very few particles hit the right boundary, so that the truncation is not having a severe effect on the behavior of the process. And then second, we hope that for the particles that do not hit the boundary, the second moment of the number of particles is small relative to the square of the mean, or that the variance is small relative to the square of the mean, so that we can get law of large numbers behavior for the particles that don't hit the boundary. But it turns out that for this process, when we kill particles at 0 and at L, neither of those things happens. The variance is actually the same order of magnitude as the square of the expectation, which is not enough to conclude that the number of particles stays close to its expectation. And also, the expected number of particles that hit the boundary is of order 1. And so the truncation will affect the behavior of the process, even in a typical realization. It's natural to pursue what happens if we move the boundary by a little bit. And suppose instead of killing particles at L, we kill them at L plus A. If we let A go to minus infinity, then we can get the number of particles to stay close to its expectation. But then the number of particles that hits the boundary goes to infinity. We could also try letting A go to plus infinity, and then the probability that a particle hits the right boundary tends to 0. But then the variance gets large relative to the square of the mean, and we lose control of the particles that stay below the boundary. So nothing quite works. And the reason is that in this model, we don't actually expect to see law of large numbers type behavior, not even after a phase of initial randomness. Because what we expect instead is that there are these occasional events when a particle gets very far to the right and produces a random increase in the total number of particles. So to get a fuller understanding of the behavior of this process, we really need a different idea. And so what we're going to do instead is to stop particles when they reach L minus A when A is large. So we're basically going to choose this first option here, and that's going to give us good control over the particles that avoid the boundaries. But then when a particle reaches L minus A, instead of killing the particle, we're going to continue to follow the descendants of this particle along until they reach L minus A minus Y, where Y is large. And then we're just going to reincorporate these descendants back into the process. To make this kind of idea work, we need to have a good understanding of what happens to the particles after they reach L minus A. And the analysis of these particles is based on a certain continuous time branching process that was first studied in connection with branching Brownian motion by Neveu in 1987. Let's consider branching Brownian motion. I'm just going to take the critical drift here of minus the square root of 2, started with one particle at L minus A. And then after we've constructed this process, we can fix a positive number y, and we can ask ourselves, if we killed particles when they reached L minus A minus Y, how many particles would have been killed? And we'll call that number m of y. And it's not hard to see that this process that we get by varying y is a continuous time branching process, because conditional on the number of particles that reach L minus A minus X, each of the m of x particles that reaches L minus A minus X will independently produce a certain number of descendants that will later reach L minus A minus X plus Y. And by the spatial homogeneity, the number of such descendants produced by each particle has the same distribution as m of y. And that's exactly the branching property. Now, it turns out that the offspring distribution of this branching process has finite mean, but thinking back to the Keston-Stigam theorem from the first lecture, the offspring distribution is not in the L log L class. Nevertheless, the Senator-Heide theorem guarantees that there will be a scaling under which we get a non-trivial limit. And Neveu showed that y times e to the minus root 2y times m of y converges almost surely as y goes to infinity to some limiting random variable w. And we do have some information about this random variable w. For example, this refers to the Laplace transform. So the expected value of e to the minus e to the root 2 u times w is given by some function psi of u, where psi satisfies this differential equation here. And that happens to be the differential equation that describes the traveling wave solution to the FKPP equation. Now we're going to need here a result about the tail behavior of this random variable w. And so this result here appears in our paper. Pascal Maillard then gave a more direct proof, and a very similar result also appears in this 2009 paper. And the result simply says that as x goes to infinity, the probability that w is greater than x is asymptotically a constant over x, where the constant happens to be 1 over the square root of 2. I also want to mention here that this random variable w is precisely the limit of the derivative martingale, which we called z in the previous lecture. So it's really just another way of getting at the idea of how big does the branching Brownian motion grow in the early stages. So how does all of this lead to the connections with Nevers' continuous state branching process and the Bolthausen-Schnittmann coalescence? Well, we've calculated that the time that it takes for a particle to reach the level L is of order log n cubed. And also the rate at which particles hit the level L is going to be proportional to this measure of the size of the process at time t. Now, if a particle does hit L, then its contribution to the process a long time into the future is going to be roughly proportional to the number of its descendants that hit L minus y when y is large. And therefore, it's going to be roughly proportional to this limit random variable w. And because of our result on the tail behavior of w, one can see that the probability that this normalized version of the size of our process, the probability that this size jumps by at least x at the time that a particle reaches L is going to be proportional to 1 over x. But the point is that this exactly matches Nevers' continuous state branching process. For any continuous state branching process, the rate of jumps of size at least x is proportional to the value of the continuous state branching process, just as the rate at which particles reach L is proportional to Zn of t. Also, for any continuous state branching process, the rate of jumps of size at least x is proportional to the Lévy measure from x to infinity. Nevers' continuous state branching process has the Lévy measure has a density proportional to y to the minus 2. So if we integrate that from x to infinity, we get x to the minus 1. And so it's really this result about the tail behavior of w that leads to the connection with the Bolthausen-Schnittmann that leads to the connection with Nevers' continuous state branching process, and therefore tells us by the arguments in the first lecture that the genealogy of the population is given by the Bolthausen-Schnittmann coalescence. Now, I want to state one more result about this process before we move on to some variations of this model. And that pertains to the question of what the configuration of particles looks like at a typical time. So that tells us about the fitness distribution of the individuals in the population, which is one of the things that we've been interested in. Now, we've already seen the key idea, which is that the density of particles near y is roughly proportional to e to the minus rho y times the sine of pi y over L. But making this idea rigorous is a little bit more complicated than one might think. And there are actually two different theorems here because this heuristic is actually capturing the behavior on two different spatial scales. And I should mention that we actually reported the proof of this result in a slightly different setting where the drift was exactly critical, but the proofs would carry over just the same to the setting that we're looking at here. So let's let t be some constant s times log n cubed. And then we will define the empirical distribution of the particles at time t. We'll call that chi of t. So we're placing a unit mass at the location of each particle, and then we're dividing by the total number of particles so that we get a probability measure. And then as n goes to infinity, these measures chi of t converge to the probability measure on the positive real line, whose density is given by 2y times e to the minus root 2y. So this empirical distribution chi of t is dominated by particles that are within order 1 of the origin. Most of the particles are very close to the origin. And because of that, we're able to see the exponential decay here. But we don't actually see the sine function because the sine is just linear near 0. And so we just see that the density is proportional to y. Now, to understand the configuration of particles farther from the origin, we can define a different point measure. So let's define also this point measure eta of t, where for a particle located at x, we're going to place a mass of e to the rho times x at the location x over L. So we have scaled the space so that the particles are going to mostly land between 0 and 1, and we're giving additional weight to particles far from the origin, so that this measure will be dominated by particles that are order L away from the origin. And these probability measures eta of t converge in distribution to a limiting measure nu, where nu is the probability distribution on the unit interval whose density is given by pi over 2 times the sine of pi y. So this time we don't see the exponential decay because we had the exponential weighting here, but we are able to see the sinusoidal shape. Yes.
So these are both for the model where you just have absorption with a subcritical slope, so the survival is possible. Is that what I'm saying?
So the way I stated them here, this is with the slightly supercritical slope so that we can survive in the long run. Right, but the place these results are actually proved for is when we have, or the proofs are published is where we have a critical case, but the particles started far away from the origin, so that you can look at this before the process is going to die.
Thanks.
Yeah.
So I'm just curious about the fact that the limiting densities don't show any dependence on S, and I'm wondering if you can comment on that.
Yeah, so basically what happens is that the particles settle into a kind of equilibrium configuration after a time which is of order log n squared. And here we're looking at a time scale of order log n cubed. And on that time scale, you see fluctuations in the number of particles from the jumps in the CSBP, but the configuration of particles stays very much the same when you normalize by population size. So we have been approximating our population model, our model of a population of size n, by this branching Brownian motion process. And we've done this because allowing the individuals to branch independently simply makes the model easier to study. Nevertheless, it is possible to make some progress on branching Brownian motion models in which there are always exactly n particles. And I want to mention first here some work due to Pascal Maillard. He introduced a process which is sometimes known as the n-BBM. So here we begin with n particles chosen at random from this equilibrium density. Each particle independently moves according to one-dimensional Brownian motion. Each particle gives birth at rate 1. And then at the time that a particle gives birth, we choose the leftmost particle, which we interpret as being the particle with the lowest fitness, to be killed. And so now the number of particles is always exactly equal to n. And so it's a more faithful representation of the original population model. So we can define this drift rho in the same way as before. And for alpha between 0 and 1, we'll let q alpha of t be the alpha quantile of the locations of the particles at time t. So that's just the value such that a fraction alpha of the particles lie above that level, and a fraction 1 minus alpha of the particles lie below that level. And then we'll let m alpha of t be this quantile q alpha of t minus rho times t. So that's just doing the right centering. And Maillard showed that the finite dimensional distributions of this process m alpha, where we scale time by log n cubed, converge as n goes to infinity to the finite dimensional distributions of a certain Lévy process. This Lévy process is a process with jumps. Lévy measure is the image of the measure with whose intensity measure has density, whose Lévy measure has density x to the minus 2. So it's the image of that measure by the map which sends x to the log of 1 minus. Now this measure here is the same as the Lévy measure associated with Nevers' continuous state branching process. And so what's really going on is that when a particle moves unusually far to the right and produces a large number of offspring, then if it produces enough offspring that in the previous model, the process Zn would jump by x, what happens is that the traveling wave moves forward, kind of jumps forward by the amount log of 1 plus x. So we can see from this result that we see the rho as being the speed of the traveling wave. We see the log n cubed time scale. One assumes that the genealogy of the population in this model would be given by the Bolthausen-Snittmann coalescent as well. but that has not been proved. There have also been some other results recently on the NBBM due to Damasi, Ferrari, Persuti, and Soprano-Loto. They considered the same model, but started with n particles from some arbitrary density. They showed that the empirical distribution of the locations of the particles at time t converges as n goes to infinity to a probability measure with density u of t comma x. This density is the solution to this free boundary problem here, provided that a solution exists. So this equation here is basically looking like the heat equation, but then we add in this u to account for the branching. And this equation holds in the interval from some LT to infinity, where LT is basically representing the left edge of where the particles are located. This equation just says that the particles start from density F, and then this says that the density is 0 at the left edge and integrates to 1. There was a missing piece here, which is that they didn't show that a solution to this free boundary problem exists. However, Barosticki, Brunet, and Pennington completed the picture by showing the existence of a solution to that free boundary problem. And one thing I want to note here is that this is significantly different from the other results that we've looked at, in the sense that what they're looking at here is the empirical density of particles when we fix the time t, and then let the number of particles n go to infinity. And that's different from fixing a large number of particles n, and then thinking about what happens in the long run as t goes to infinity. In the remaining time, I want to briefly mention two other variations of these population models, which we believe have genealogies that would be described by the beta coalescent rather than the Bolthausen-Schnittmann coalescent. So the first is a generalization of the model due to Brunet, Derrida, Mueller, and Meunier that I mentioned earlier. This generalization was proposed by Cortinez and Malin. And what they did was to say that, they fixed a number a between 0 and 1, and they said that an individual located at x produces offspring at the locations a times x plus yi, where the yi's, as before, are the points of a Poisson point process on the real line with intensity e to the minus y. So if a is equal to 1, we get the model that we looked at before. If a is less than 1, then the locations of the offspring are shifted towards the origin relative to the location of the parent. But as before, we're going to keep the n fittest particles, the n rightmost particles, to survive to form the next generation. This time, the offspring of a particle at x are the points of a Poisson process with intensity e to the ax times e to the minus y. In the same calculation that we did before, we see that the fraction of the population in the next generation from a particle at xi is proportional to e to the a times xi. Now let's let alpha equal 1 over a, and let's ask how likely it is that there's an individual with such that e to the a times xi is bigger than z. The same as xi being bigger than alpha times log z, and from this e to the minus y structure in this Poisson process, the probability that this happens is going to be proportional to e to the minus alpha times log z, which is z to the minus alpha. Now, before we had z to the minus 1 here, which was the signature of the Bolthausen-Schnittmann coalescent. But if alpha is between 1 and 2, this z to the minus alpha is the signature of the beta coalescent with parameters 2 minus alpha and alpha. So here's the precise result due to Cortinez and Malin. Let's sample lowercase n individuals from the population in, let's just say, generation t. Psi n of k will be the partition of 1 through n, whose blocks correspond to groups of individuals with the same ancestor when we look back k generations. If a is between 0 and 1/2, then the particles are pushed very strongly towards the origin. Selection has very little impact, and the genealogy converges to Kingman's coalescent exactly as in the Wright-Fisher model. If a is equal to 1/2, the genealogy still converges to Kingman's coalescent, but we have to speed up time only by n over log n rather than n. Then if a is between 1/2 and 1, then if we speed up time by n to the alpha minus 1, these ancestral processes will converge to the beta coalescent with parameters 2 minus alpha and alpha. And if A is equal to 1, then we recover the result of Brunet, Derrida, Mueller, and Meunier, which is that after speeding up time by log n, the genealogy converges to the Bolthausen-Snittman coalescent. Now, of course, those results apply only to this very specific model, but based on these results, Cortinez and Malin conjectured that the beta coalescent should also give the genealogy of the branching Ornstein-Uhlenbeck process with selection of the n rightmost particles. So this would be the same as the n BBM, but with the particles moving according to the Ornstein-Uhlenbeck process rather than Brownian motion. This is something that I have looked at a bit, and I do believe that this conjecture is true, at least for some variants of the branching Ornstein-Uhlenbeck process, but at the moment, we have nothing rigorous to report on that problem. Now, the other model that I want to briefly mention was introduced recently by Julie Tournier as a model of so-called semi-pushed front. So it's similar to the original branching Brownian motion model. We're going to start this time from n particles located at 1. The particles independently move as one-dimensional Brownian motion with a drift of minus rho, and particles are killed if they reach the origin. But instead of all particles branching at the same rate, we're going to say that particles between 0 and 1 branch at rate beta over 2, where beta is greater than 1, and particles that are above 1 branch at rate 1/2. Rho here depends on the choice of beta, and just as in the model that we discussed where the particles all branch at the same rate, we choose the drift in such a way that the process is critical in the sense that the size of the population stays as stable as possible over time. This process is actually modeling what's known in biology as an Allais effect. We are used to the idea that of thinking that in regions of high population density, competition will suppress population growth. But the Allais effect is that in regions of low population density, it's also possible that population growth could be inhibited. And so in this model, we expect that most particles are going to concentrate towards the origin. So that's where the branching rate is higher, whereas the particles far from the origin are likely to be in a region of lower density. And so we set the branching rate to be a bit lower. Now, Birzu, Halusjak, and Korolev had argued that the Allais effect in certain circumstances can produce beta coalescent genealogies. So in certain circumstances, the Allais effect can cause the genealogy to be a beta coalescent rather than a Bolthausen-Snittman coalescent. They proposed that this could happen, for example, if the population is expanding into a new geographical area. The idea being that the leaders that get far ahead of the others are in a region of lower population density, and so they're not able to necessarily produce as many offspring. So here is a theorem due to Tournier. She showed that for beta in a certain interval between beta 1 and beta 2, if we keep track of how the number of particles in this process evolves over time, where we speed up time by a factor of n to the alpha minus 1, and we scale the number of particles by a constant over n, then the finite dimensional distributions of these processes converge as n goes to infinity to the finite dimensional distributions of the alpha stable continuous state branching process. Here, alpha can be any number between 1 and 2, depending on what's chosen for the value of beta. Now, because of the connection between Nevers' continuous state branching process and the beta coalescent, so we saw in the first lecture that the beta coalescent describes the genealogy of the alpha stable continuous state branching process, one would expect that the genealogy of the population in this model should also be given by the beta coalescent with parameters 2 minus alpha and alpha, but so far that has not been proved. And as in the case when all particles branch at the same rate, the proof of this result proceeds by stopping particles when they get to a particular level L, and then following the descendants of those particles carefully to see how big of a jump in the total number of particles those particles are going to create. And so the key to understanding why the alpha stable continuous state branching process arises is this theorem here. So notice first that because the branching rate is lower near L in this model, Basically, this means that the drift is going to be larger relative to the branching rate. And so if we scale things to keep the branching rate the same, the drift is going to be larger, and in particular, the drift is now going to be subcritical. And so this theorem here is, it complements the result that we saw due to Neveu in the critical case. The result was stated in close to this form in Tournier's paper, but the key ideas were already in this earlier work of Chauvin and of Quansheng Liu. So we consider branching Brownian motion with drift of minus rho, where this time rho is greater than 2, so this is now subcritical. And we're just going to start with one particle at L. We'll let m of y be the number of particles that reach L minus y if we kill particles when they reach that level. And then the theorem says that as y goes to infinity, e to the minus this constant times y times m of y is converging almost surely to a limiting random variable w, which happens to be the limit of the additive martingale. And furthermore, we have this result about the tail behavior of w. The probability that w is greater than x is asymptotically a constant over x to the alpha as x goes to infinity, where alpha is given by this number here. And it's this result about the tail behavior of w where we see this x to the minus alpha power arising that tells us that the jump rates for this process should match up with the jump rates of the alpha stable continuous state branching process. So that's all I'm going to say for today. So in the next lecture, we will discuss a little bit the branching Brownian motion with absorption when the drift is exactly critical. And then we're going to move on to the other of the two population models that I introduced in the first lecture. Thank you.
So are there questions, or you don't have a microphone? But... Okay, so there seem to be a couple of questions, so maybe you start.
So I think you showed us 3 results for convergence to a continuous state branching process, one for this last model, then the result by Maillard, and then the one in the very beginning. And in all 3 of them, the convergence was in finite dimensional distributions. And now the natural question would be, well, can we also show tightness and then get process level convergence? Or is this very difficult in this setting usually?
Okay, so if you want to get the usual kind of process convergence, which would be convergence in the Skorohod sense, it's definitely false. Okay. And the reason for that is that the continuous state branching process makes abrupt jumps. Whereas these population models, what you have are one individual being born at a time, but it happens over a very small time window. And so it kind of jumps up gradually. And so when you try to look at the distance between those functions in the Skorohod metric, it just doesn't go to 0. Now, what might be the case is that there might be some other topology that would be more natural than just finite dimensional distributions. I know of one paper where in a similar setting, they used a different topology called the Meyer-Jang topology and proved convergence under that topology. One could also look at something like the Skorohod M1 topology. But I think part of the problem is that these papers tend to get so long that we don't want to make them longer by getting fancy about the topology. But the upshot is it's probably possible to do better than finite dimensional distributions, but definitely not the J1 topology.
I think there was a second question.
So you mentioned this conjecture that for the Ornstein-Uhlenbeck setting, the alpha stable genealogies would appear. Yeah. I wonder, I mean, the alpha, would it then be related to the drift diffusion relation of the Ornstein-Uhlenbeck process?
Yes, it would have to be related to how strongly it's being pushed towards the origin. Right. That's right. Yeah, that's the conjecture.
Right. Thank you.
Are there further questions? Are there questions online? Okay, then I think we can thank Jason again.